Good day, ladies and gentlemen. During our last lecture, we more or less looked at the applications of differential equations, and more specifically, we talk about how to use differential equations to discuss time path in market models. Today, I would like to introduce you to a new sort of topic, and that is difference equations. I'm just going to talk about difference equations and how to solve simple difference equations, and then I think during our next lecture we are going to look at the applications in economics. Now, this is the overview and the specific sort of topics that will be discussing. The reading list remains more or less unchanged. Now, what is a difference equation? Now, this is any equation that expresses a relation between a dependent variable and a lagged independent variable which changes at a discrete time interval. So there are two things. There is a dependent variable t, that depends on a certain variable y, that is I here, depending on a certain variable y, which is determined the previous year. Notice that here we're talking about discrete situation. So like we're looking at what happens this year and the relation that it's got with another variable the following year, or it can be the year before the following year. So in this equation, you can see that investments in time t depends on your income in time t minus 1. So how much are you going to invest this year? It will depend on the income that you earned last year. So the income that you earned last year or investment that you make this year depends on, or is a function of the income that you had last year. We can have so many examples. For example, savings. How much would you save this year? Depends upon how much, your income last year, all right? Or we can even have something like this, where your investments you're making this year depend on the certain constant, and then also depend on the income that you made last year. So what happens is that you have a dependent variable this year that depends on another variable that happened the previous year or the year before the previous year. Now, how do we identify, differential equations? You recall that when we discuss difference equations, when we discuss differential equation, we try to name differential equations using the degree and the order, okay? Now, in difference equation, we use only the order to name a difference equation, right? And when you talk about the order of a difference equation, it refers to the maximum number of lags that you can find in the difference equation, right? So if you look at this one, the maximum number of lags is 1, okay? Because what happens this year depends on what happens last year. So it means that this is a first order difference equation. If you look at this equation, what happens this year, that is investment this year, depends on income, that one earned the year before last year, that is 2 years back. So we call this one, second order difference equation, because the maximum number of lags is 2. So once you see the number of lags, you are easily able to identify the difference equation. It also pays to talk about, homogeneous and non-homogeneous differential equation. If you look at this general form differential equation, for example, if this value of c, if the constant here is equal to 0, we call it a homogeneous differential equation. And when it is not equal to 0, then we call it a non-homogeneous differential equation. You will come to know the reason why we need this homogeneity condition, when we discuss the time path in difference equations. So I'm giving you more example. There's a first order homogeneous difference equation because there is no constant. Now there's a second order because this is equal to 2, and this one there's a constant here, so there's non-homogeneous difference equations. Take your time and name these differential equations and try to go through this activity, please. Now the other thing I would like to talk about is about how to solve a difference equation, right? What I'm going to do is that I'll first introduce you to a very simple sort of solution called the iterative method. And once we are done with that, we can talk about how to cross-check your answer. And then we will look at the general solution for any first order, first degree difference equation. So let's look at the first one, the iterative method. In this method, what we'll do is that when you have any difference equation, you put in successive values of 2, okay, or of the t. So t can take value from 0, 1, 2, 3, and then you study the nature of the solution, and then out of that you generalize. It's a little confusing to you, I believe, but then let's take a specific example where I can explain what I'm talking about. Look at this equation. We are supposed to find the solution to this difference equation, okay? This is a difference equation, and we are supposed to find the general solution, right? Now, this is our equation. If t is equal to 0, so we put a 0 here, so we get y1 is equal to our c, which is constant, plus 0 here, so we get y1 to be equal to c y0, okay? Now, when t equals to 1, it means we put 1 here, so we get y2, we put 1 here, which is equal to c y, 1 over here. But then you could see that from equation 1, which is this equation 1, when t is equal to 0, y1 is equal to that. Hence, we can insert the value into equation 3. So when we insert it, so from here, y2 is equal to c y1 as is over here. But this y1, we know from here, right? This y1, we know from where it's equal to c y0. So when we evaluate, we get c2 y0 here. Now, again, when t equals 2, we put a 2 here, we get this equation, c y2. But we know that the value of y2 is equal to this. So we can slot the y2, so we have from this y3 we know is equal to this. So our c is constant. Then in place of this y2, we put the value of y2 over here. So we get y3 should be equal to c raised to the power 3 y0. It's quite clear that from here, you can do the same for y4, okay? And then you slot in y3. And from here, you can see that when y0, when t is equal to 0, we had some values over here, right? And it goes on, and we can generally have the solution that y is equal to c raised to the power t y0, okay? When t is equal to 0, sorry, these ones should be shifted up. When t is equal to 0, y1 is equal to c y0, okay? When t is equal to 2, y3 is equal to c raised to the power 3 y0. And then here, when t is equal to 1, we get this. And t is equal to 4, we get this. So straight away, it helps you, you can generate the solution that y is equal to c raised to the power 4 y0 is the solution for y4. And therefore, the general solution is equal to y equals to c raised to the power t y0. So the iterative method involves putting in successive values of t and then deducing the general solution once you've been able to assemble all the solutions that you get. So what we need to do is just raise these ones up here to correspond to the t here. Now, another example, look at this one. Zt is equal to 3zt plus 1. Sorry, it's equal to 3zt. And we've been given a boundary solution, a boundary point, z0 is equal to 3. Now, here, as I said, we put in successive values of t and try to generalize the solution. So when t is equal to 0, we have, z, 0 plus 1, which is equal to 3z0. So it means z1 is equal to 3z0, okay? When t is equal to 2, when we slot in z2 is equal to 3z1, which is equal to, it implies that z2 is equal to 3 dot 3z0, because what we have standing over here, because z1 over here is equal to what? 3z0, and there's the 3z0 over here. So this gives us 3 squared z0, right? When t is equal to 2, so we have z3 here to be equal to 3z2, but we know z2 is equal to what? z2 is equal to 3 raised to the power 3 squared z0. So when we insert it, we get z3 to be equal to 3 raised to the power 3 z0. So looking at the solution, we can generate from this iterative method, we can easily see that the solution zt is equal to what? 3 raised to the power t z0. So this is the solution to our equation. Now, how can you cross-check your answer? It's very easy to do that, right? Let's look at it with a specific example. In the two examples that we have discussed, the first one, we had this equation and we said this is the solution, right? Let's see this, if this our solution satisfies this equation. It means if it's really a true solution of this equation. What we do is that we take this equation, right? And then we can take any two successive values, t0, t equals 0, t equals 1. I've taken t equals 0, t equals 1 just because of what? Simplicity. You can take t equals 3 and t equals 4, right? The only thing is that when you take t equals 3 or t equals 4, it makes your analysis, you are going to do more calculations. But when you take very simple values here, it's going to be quite, easier. So when t equals 0, right, we get y0 to be equal to c0, y0. Any number raised to the power 0 is 1, therefore we get y0. When t equals 1, we get this, we slot it into the solution. We are slotting t equals 0, t equals 1 into the solution that we have, all right? So we get these equations, right? y0 equal to y0, of course, and then y is equal to cy0. Now, this is our original differential equation. What it means is that when we take these successive values, okay, y1, and then we slot it here, and then we maintain this c, and then we put in y0, they should be equal. If they are not equal, it means our answer is not correct. So what it means that here, when I take this my y1, okay, so we took successive values. So if this is equal to t1 and this is equal to t0. So my y1 here is equal to cy0, right, which comes from this side, and this is equal to our c. This is my c. This c is the c1 here, and this is equal to, and then we add our y0 here. This is the y0. So we are saying that the left-hand side of this equation is equal to the right-hand side. So it means y1 is equal to cy0 in our equation. So this is our y0. And then we see that cy0, which is over here, is equal to cy0. It means our answer is correct. Now, let me come straight to the general solution for the first order linear difference equation. When you talk about first order linear difference equation, this is of the form that we see here, where b is a constant, a is a constant. So you see, the variable yt being expressed in terms of the variable yt minus 1. When you have a linear difference equation of this form, now this is the general solution. In a situation where your b, this is your b, where your b is not equal to 0, this is the solution. The yo here is a constant that is always given. The a and b are the coefficients that you have standing here. Okay, so whatever value is here, you put it there. And in a situation where b equals 1, then this is the general solution. And implicitly, if we decide to say that, there's a constant, what is standing here is a constant. If you give it a constant a, what is standing over here, which is what is standing over here, we give it a constant c, then the general solution can be written in this form: yt equals ab raised to the power t plus c. Okay? In many cases, what happens is that this is a definite solution, right? If the value of this initial condition, the y0, is given, then we get a definite solution. In many cases, when it's not given, sometimes we can have a constant which would help us to define this solution. Now, let's look at an example with this formula. And here, to revise all what we've discussed till now, we are supposed to solve this equation. Our boundary point has been given, and we are supposed to also cross-check our answer, all right? So when there's a solution, when we take the equation, this is the equation that we have, okay? Now, we can reorganize it, so there's a general solution. So if we put the equation, so the equation that we have over here, So when we send this additive to the other side, we get this. Just that we want to express it in the normal form that we expressed a first order linear difference equation. Now our b is equal to -4, our a is equal to what? 7. We said that, and our z0 is equal to 4, which was given. And we said this is our solution in this case, z0 minus a. So this is the general solution because we have b not being equal to 1. So the next thing is that I put a and b into this equation, and I simplify, and then I get this equation. Okay? I simplify, and I get this equation. So this is the solution of our difference equation that we have over there. The next point is that we are supposed to cross-check our answer. So we have this equation, okay? I will take any successive values. As I said, take t equals 0, t equals 1. I can take t equals 2 here, then this is equal to 2 equals 3. So the values to be successive based on the number of what? Lags. In this case, this is a first order difference equation, so the lag should be, the largest lag length should be 1. Now in this equation, if zt equals 0, so it implies that I put 0 here, right, and I evaluate it, I get 4 here. Okay? When I put t equals 1, it means I put t equals 1 here and evaluate this, and I get -9. The next point is that this -4 and -9, when I put it into this equation, they should be equal. Notice that zt, in my situation, the t was 1, and I got -9 over here. This is equal to my -4, which is a constant here. The z0, in our case, is zt minus 1, is 4 over here, and this is my constant 7. You see that when I, simplify this, I get -9 to be equals -9, suggesting that our equation, our solution is correct. Please take your time and go through these activities, and let's meet at the chat room if you do have any further questions. Right, the next thing that we need to talk about is about the dynamic stability of our equilibrium. And the argument goes in the same way, that when you have this equation, right, and there is some destabilization, in the long run, are we going to get back to equilibrium, right? So when we talk about dynamic stability, we talk about how the solution of a first order difference equation behaves as time increases beyond bounds. That is, as time tends to infinity. Right, let's look at this. Now look at this, our equation. This is the solution, right? This is the solution, and in this solution, it's made out of 2 components. This component, and then this component, the ABT component and the C component. Actually, we call this one the complementary function, right? And then we call the C here a particular solution. Now, if we look at this general solution, we say that this equation is dynamically stable if the limit as ABT, the limit of a b raised to the power t, as t tends to infinity, is equal to 0. What it means is that this is the initial sort of particular solution. This stabilization in this particular solution is caused by this complementary function. So the question is that in the long term, as t approaches infinity, will this additive tend to 0? If it will tend to 0, then it means there is dynamic stability. If not, it means our solution is not dynamically stable. So let's investigate the behavior of this function, b raised to the power t. For simplicity, I will suggest that let's allow our constant a to be 1, and then our constant c to be equal to 0, so we have only a function of this nature. Let's look at how this function behaves. What I've done is that I've investigated these functions for different values of b. Okay, when b is greater than 1, when b is equal to -1, b is a fraction, b is less than 1, etc. We can write them in absolute values like this, and then I've chosen specific values. So for example, when b is greater than, is greater than 1 here, we can have this value 2, because 2 is greater than what? 1. And then we have managed to find the values of this b raised to the power t for different values of t. Okay? For different values of t. We just want to see how the function behaves. So for all these functions, these are the values that we get when we try to slot in the value of t. Now, for the first one, okay, and here I'll just explain, let's say 2 of them, and then the other ones you can take your time and go through. So we have here 2 raised to the power b, right? Sorry, 2 raised to the power t. For different values of t, we get this value. Now, what you could see is that when t is equal to 1, this function y equals 2 raised to the power t is increasing. So what it means is that if t tends to infinity, this function will also go to infinity. So this function will never come to what? 0. Right? So what we say here is that the function diverges. Right? It doesn't tend to 0, it diverges. If we take the other one, for example, and here I mean this one, right? You see it's 1 throughout. So again, when it's 1 throughout, it's constant, and we get this equation. When you look at this one, what is half? You see that as t increases, this value tends to what? 0. Okay? 1 raised to the power anything gives you 1. If t comes down here, 2 raised to the power infinity, 1 over 2 raised to the power infinity in the long term can give you 0. Okay? We can do that. You can see that for all the other values that... There are 2 things over here. You see that when you take this one negative, for example, the value oscillates. Okay? It goes through negative, comes to positive, negative, positive. But one thing you could see is that it is turning towards 0, but it's just oscillating between positive and negative values. Right? So that's what we get when you get minus 1. In the long run, we can summarize it as follows. If the absolute value of b is greater than 1, then the time path diverges. That is, the function tends to infinity. If the absolute value of b is less than 1, then it means the graph tends to what? 0. Also, if b is greater than 0, then we have non-oscillating. It means it either stays in the positive direction, or the positive quadrant, or the negative quadrant. It doesn't rotate between the positive and negative quadrant. But then when b is less than 0, then we see the function rotating within, the positive and the negative quadrant. In a gist, we use these 2 things to describe the time path. It can converge or diverge, or it can oscillate, or it will not oscillate. So when you look at the function over here, now what we've done is that we know the value of this function now. We are saying that this function, it can converge, it can diverge, it can oscillate, it can also not oscillate. Now, if we add the value here, what is the value of a going to do to this function? Notice that initially we assumed that a is equal to 1, right? Assuming a is not equal to 1. This value a here is a scale factor, right? It either increases, expands the value that we go here. So you multiply the value that we get here by a certain factor, so it expands it, all right? Now, what is the value of this c here? The c here draws this function up, or it draws it down. So when we combine these 2, that is the a and the c, all what it means is that what matters is the behavior of this function. This one will scale it up or scale it down. This one will move it up or move it down based upon the value of what? C. So what we can conclude is that there can be dynamic stability, or there wouldn't be dynamic stability. It all depends on the value of b that we have over here. So b is the most important factor that would determine the dynamic stability of any first order difference equation. Right, let's look at some example. This example, more or less, here we are trying to do all what we have discussed this morning. Let's consider this difference equation. We have been given the boundary points. We have to find the solution, cross-check our answer, and then investigate the dynamic stability of this equation. Right, so let's look at the solution. We have this equation here, all right, we can simplify it, by dividing through by 3. We get this equation. It means that our A is equal to 0, our B is equal to this. Straight away, B is not equal to 0. We can write our general solution. This is our formula for our general solution. We insert the value of A, B, and Y0, right? And we have something of this nature, which simplifies to this. Now, the next point is to cross-check our answer. If t is equal to 0, we get this. If t is equal to 1, we get this. Notice that it means we have y1 should be equal to this, multiplied by that. So when we put our y1, which we obtain to be this here, we get this. Okay, and then, and then our 4 over 3 is over here. This is our 4 over 3, this is our y0, right? So this is our 4 over 3, this is our y0. So you see that we have the same things here. It means our solution is correct. The next point to investigate the dynamic stability of this equation, notice that in this situation here, our B is equal to that, right? And the absolute value of B, which is 4 over 3, is greater than 1. What it means is that B is positive, so it is not going to what? Oscillate. All right? If it were to be negative, then there is going to be oscillation. Now, the second point is that 4 over 3 is also greater than 0, meaning that our function will not converge. So what it means is that this equation is not dynamically stable because it tends to infinity as t approaches infinity, and also it does not, oscillate. So this is the solution to our example. Please try your hands on these activities, and I hope if you have any problem, let's discuss it at the chat room. Thank you.